delighted that you're all here today. Sorry, I apparently have no idea how to use a microphone. Excuse me. I also feel like I need to apologize for naming this presentation so very vaguely. If you're expecting anything large or new, you're not going to get it here. I'm not talking about Webpack or Node or freaking Kubernetes or anything. I'm going to talk about small things and old things. And coming back to the title, we're going to be building bits of Ruby using Ruby. So we're going to identify two small bits of Ruby that we're going to construct using Ruby, but not the bits that we're constructing. It's a bit like a game, you see, where we're limiting ourselves and trying to build the things that we're limiting ourselves from. Anyways, so getting on with it, the two bits that we're building are Boolean values, you know, sort of like true and not true and false and not. You get the idea. And the other thing is natural numbers. That's 0 and 1 and 2 and 13s in there, and, you know, whole positive numbers and 0. So starting off with Boolean values, we're going to have to go back to starting somewhere in the end of the 1960s, mostly in the 1970s, and then the 80s, to get an idea of how to sort of effectively implement this. We're going to be talking about Smalltalk, the language. Actually, just out of curiosity, has anybody here built anything with Smalltalk? Yes, lovely. So excited that someone knows more syntax than I obviously do. So Smalltalk was developed at Xerox PARC. That's the Palo Alto Research Center during the 1970s, and it was released to the public in 1980. It is the epitome of an object-oriented language. Like, you have no idea. Like, people say everything's an object in Ruby. Like, everything is an object in Smalltalk. It's insane. So they're so confident in this idea of everything being an object that they only have 6 keywords. Up until today, there's only 6 keywords over there. And it's a bit weird for an object-oriented language not to have a class keyword. How the hell do you make a class? Well, it turns out there's an object that's around the whole time called object. And you call a function on it, call a method on it, to build a new class. And from this class, you create new instances which are more objects. And the class you created is another object. So this might sound a bit familiar if you followed, because I kind of didn't. It's similar to the Ruby object model. And Ruby got a lot of things from Smalltalk, a lot of inspiration. But one thing it did not take is the if keyword. Because Smalltalk doesn't have an if keyword to take, which upset me greatly. How the hell do you do flow control? It turns out by message sending or calling methods on things. So it's an object-oriented language, so you kind of expect true and false to be objects. That is the case. And if you want to execute some code if something is true, then you tell the value true to execute this code if it is true. Or you can tell the value true to execute some code if it's false, but then it won't. Does that make sense? Like, yeah, it's just sort of things interacting and stuff being defined by what they do rather than what they are, which is a very powerful thought. Anyway, so here's a conditional statement in Smalltalk. The syntax looks a bit weird, but if you're familiar with Ruby, which I freaking assume you are, it's not too hard to get into. So true over there is an, oh, I can use the shadow. True over there is, shh. True is an object. If true is a message being sent to true. Now, message sending is a sort of Smalltalk parlance for calling a method. So method on true, and everything after the colon is the argument. These square brackets is how you define a block in Smalltalk, and the stuff inside the block is some more code to execute. So strings are objects, they have methods, specifically print new line, which is called on the string, and if true is true, which it is, executes the block, and prints that. So that's quite straightforward, isn't it? It sort of reads nicely, and it gives you an idea of the identity of things. This is a sort of transliteration of this line of code into Ruby, which you obviously can't do. True doesn't have an if-true method, and string doesn't have a print method. A lot of smart people have spoken about how you'd implement this in Ruby. Like, I think Yehuda Katz said a bunch of stuff about it, and Sandy Metz definitely mentioned it. But like, you'll have to, in order for the if-true type 5 thing to work, you'd have to monkey patch true class, false class, object, and null, I think, which is a bit excessive. Also monkey patching all over the shop. So we're not going to do that. We're going to build our own true and false classes. So let's start off with that. We've got a true and a false. And just as we described before, if we want to do something, if a value is true, we give it that code and tell it to do it. Similarly, we can say to true, do this if you're false, and it won't do it because it's not false. The opposite is true for false. You know, it does things when you call the if-false method, and doesn't do it when you call if-true. What's interesting about this is that all these methods return self, which makes it quite useful and gives you the ability to write conditional statements like this, which looks like a regular conditional statement, doesn't it? Yeah, that sort of gives us a decent model of Boolean values. Obviously, you can extend it for negation and other Boolean operations. I'll just leave that as an exercise to you guys. It's not that hard. So now that we have a decent model of Boolean values, we can move on to our idea of natural numbers. And to do that, we're going to have to go even further back in time than the 1970s. We're going to go all the way back to, oh gosh, what's happening? All the way back to the 1930s, and speak about a guy called Alonzo Church. He was a cool fellow. So that smiley chap hung out with Alan Turing, and they wrote the Turing Church thesis together. But more importantly, he came up with the lambda calculus. And as part of that, he encoded numbers as a combination of functions. We call this church numerals these days. And this, like, is a pretty groundbreaking idea. If you think about it, like, for thousands of years, we've been thinking of numbers as this sort of fundamental thing. Like in agrarian times, we'd count apples and say we have 5 apples, and 5 is an important thing, and we can't reduce further than that because it is the amount of apples. But along comes Mr. Church, Professor Church, my bad, and goes, you know your idea of counting? Just bin it. We've got functions now, guys. Yeah. We want to build, with Ruby, an idea of numbers, which means we can't just, you know, go full-out lambda calculus on it. We just sort of need to stick with the ideas and the sort of feel of Ruby. So we're going to do it in a bit of an object-oriented way. We want to build a new number, which begs the question, what is a number? What the hell are we building, actually? So numbers are things like 1 and 5 and 6 and 7. But this doesn't really tell us much. These are just sort of names we apply to concepts. Just saying 7 without knowing how and where it exists doesn't tell us much. So from that, we can sort of infer a behavior of numbers in that they know what comes before and what comes after them. There's an ordering to numbers. So we're going to encode that by sort of nesting them. So you construct a new number over another number. So we've essentially got this stack of numbers, each of which we could give a name, or we don't have to for now. I mean, that sort of solves the question about the structure of this, but it doesn't really get to the behavior of numbers. What do we want the number to do? I mean, we want to have it convertible to an integer and junk like that. So we're going to sort of have to investigate how numbers behave. It's very convenient to do that by counting with them. So we have two containers here filled with this mediocre candy. And we want to find out what the number of these containers is. Like, how much candy do they contain? Do they contain the same amount? Does the one contain more? So without sort of knowing what numbers is, we're just going to, every time we take out a candy from this side, we're also going to take out a candy from this side. We're going to keep on doing that for, well, it seems like quite a while. But if both these containers end up being empty at the same time, then we know they have the same number. That makes sense, right? It's intuitive. We've taken out a candy of each side and they ended up being empty at the same time. If the one ends up empty before the other one, then we know it has a smaller number. The one that ends up empty last has the bigger number. So this isn't completely clear yet, but what I'm implying here is that the behavior of a number is to do something, to perform an action on something else a certain amount of times. So getting down to a bit of a Ruby implementation of it, we've got our sweet number class over there, and as we saw on the previous slide, we can initialize it with the previous number. So here we have 0. 0 is a bit special, but we'll get to that in a bit. We can call on a number to do its thing. You see it takes a block there called action. That's the thing it does to the value. So in our example over there, our value was basket of candy. And our action was take candy from basket of candy and put it on table. Say there were 5 candies in there. The first layer of the number stack would take out the candy. Then we would have a new value. We've mutated our value, which would be passed to the next layer, which is number 4, which would do that again. If we reach the last layer, which is 0, it does not perform the action. It just returns the value. So if there are 5 candies in there, and we use the number 5, at that point it would be empty. So we've got a number, but we want to confirm that this is the case. So we've got our good old 2i there to transform these to integers. We see 2 is defined by sort of 2 layers of number, and 1 is just 1 layer. So our conversion process is quite simple, actually. You see, we use the value 0, and the action increasing the value by 1, and eventually when we get to 0, the value which was mutated by each of the layers would be returned to us. So if we have some value, say 3, it would go through 3 layers. The action of increasing 0 by 1, or the value by 1, would be performed 3 times, and we'd end up with 3, which that's pretty cool. And there's a thing we haven't mentioned by now, which has been quite obvious. We've done it a few times, actually. And that is incrementing a number by 1. In fact, the implementation's on this slide, so let's just switch over. Incrementing a number is just adding another layer on the stack, wrapping it in another number. Now, this seems very trivial, but it unlocks freaking superpowers. Because we can now increment a number, we just get addition almost for free, which is very useful because now we can sort of start accessing larger numbers in an easier way. Instead of nesting 3 numbers, we nest 2 and just add another one to it. I mean, that's a silly example, but something like if we want 10, we can only build 5 and then add it to itself. So here's how surprisingly short implementation of plus. You see, I guess you guys know how sort of the operator overloading works in Ruby. Plus is just a method on the object. So the second value, what we call here other, is used as our value, and our action is just incrementing that. So say we have 2 and 3. We want to add the 3 to the 2. So this number 3 needs to go through 2 layers of 2. Each layer it goes through, it gets incremented by 1, and you end up with 5. It's simple math, right? Which, that was cool, and it was unlocked by identifying a behavior of a number, which is incrementing itself. But plus, in itself, identifies another behavior, which we also get almost for free, which is multiplication. This gets really useful if you want to get to large numbers, because, you know, it's so easy to multiply things together and get a huge number. So our simple implementation looks like this. It's a bit more complex because we depend on closures. That is the closure saving the other value that's being passed in. So we start off with a value of 0, and each layer of number it moves through, we add our other number to this value, it's sort of running total. So if you do 2 times 4, 4 is being passed through 2 layers. So the action is implemented twice, or not implemented, applied twice, whatever. Meaning we've got 0 plus 4 plus 4, which gives us 8, which is 4 times 2. Which, yeah, I don't know, I find this very exciting. So a thing that has always been a bit weird for me in Ruby is the ability to go, like, 3 times do this thing, like 3 times print hello, and it'll just go hello, 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 which is, like, it's cool, but why? I mean, can't you just use a regular loop? What is so special about just calling a method on? But discovering this, it feels almost natural for numbers to repeat things. So, you know, doing stuff like that, you'd expect 3 to be able to print something 3 times if you tell it how to print something, right? So here's our implementation of this. It firstly doesn't care about the value at all. And secondly, the argument is just calling a block passed to this method. And then it repeats that n number of times. Anyways, that's all I have for you today. Thank you very much for coming. Do you have any questions?